So I want to talk now about turbulent boundary layers, which is very, very common. So in laminar, we have streamlines. We have an ordered flow, right? If you remember the video I showed you, we have these lines that were actually hydrogen bubbles, that they were perfectly straight, they were beautiful, right? Do you remember that video that was like from the 50s or something, right? That's laminar, right? And those lines you saw, those were the streamlines. But in turbulent, actually we have a chaotic macroscopic motion, right? You might remember from fluid mechanics that you have eddies, and actually if you were to put a pressure gauge in a turbulent flow, it would give you all kind of funny fluctuations. If you were to measure velocity, you can put something such as like a weather vane, right? And you would say that like oscillate. Overall, they do have some sort of an average, right? So turbulent flow still flows. It's not that just nothing. But this average is not a smooth average. It's the average of something that is varying. This is the chaotic macroscopic motion. And now this gives us enhanced transport. I don't have any cool video to show you of this. I'll have to find something up. But think with me. So if the fluid in turbulence is like all like, well, turbulent, I don't know what better word, like has lots of velocities, like it's at the small scale, right? But moving all over the place. When we calculate transport of heat or transport of viscosity, right? And by the way, you have another class for this, but transport of mass by diffusion, right? So you have a diffusive type of process, right? Now, in the laminar case, diffusion is fine through a boundary layer. But in turbulence, right, you have this transverse motion of the fluid, this chaotic motion of the fluid. And this motion actually is advection, right? So in addition to the viscous transport, the diffusive transport, right, the thermal transport, you have this advective transport that happens at the eddy scale, right? That's the reason if you put a spoonful of sugar in your coffee, you stir it, right? Because then this turbulence mixes it up better. But if you don't stir it, it's probably going to take long for the sugar to distribute, right? That's the reason why so many chemical processes are stirred. Actually, until recently, we have a professor who has built her whole career on stirring. Right now, she's a dean in Saskatchewan, right? It's crazy, right? And the whole point of this stirring, the whole point of turbulence is that now, in addition to what is called the molecular transport, that is like things moving as if they're all in perfect order, now you have this small scale advection that move things, right? This is very important, enhanced transport. So I'm going to make a schematic of a boundary layer with turbulence. So I'm making a plate with a caveat that this plate actually represents so many things, right? And we have discussed so far a boundary layer, and I'm going to make now, let's talk about a viscous boundary layer, but I'm going to tell you more about this. So these start like this square root, right? This is what we have been talking about so far. Yet some funny stuff happens, because at some point, this flow starts to become unstable. That is what is called the onset of turbulence. And then goes full crazy. Right? And so up to here, we're going to say this is laminar flow. And everybody would agree, right? after the onset of turbulence, what we have is also turbulent. Turbulence is quite complex. I'm going to think about it in a simple way, but let me tell you some things that are present. Remember that I mentioned you have motion, for example, transverse to the overall motion. You have transverse motion that enhances the properties. Yet, if I'm very close to the surface, I cannot have a whole lot of transverse motion, right? If I have air over metal, let me tell you, the air is not going to be denting the metal. So, very close to the plate, there's no transverse motion. And for that reason, you have something that is called here a viscous sublayer. This is called a viscous and then when we break into full crazy turbulence, we have also another layer that doesn't have the full value of turbulence. And this one is called, this other layer here, it's called a buffer layer. Right. And all this is called, this part here, this is called the turbulent region. Now, this part here, the onset of turbulence, it's called a transition. And from here up here is the turbulent region. These are the vortices, right? These are the little vortices that enhance transport. Let me tell you the good news. In this class, when we say laminar, we mean this. And when we say turbulent, actually we mean not laminar, and we mean this. So we're going to talk about two parts. What is laminar and what's not laminar. And also, we're going to see all this part that is laminar, we just discussed, and this part that is turbulent, we're going to treat it as if all this sublayer and buffer layer and all those things were not there. We're just going to give it some value of convection coefficient without going all too deep into it. And that's okay. And the reason it's okay is this is deep. And it's so deep that turbulence is still one of the unsolved problems of science. There are no predictions of good predictions of turbulence. There is statistical analysis, there are rules of thumb, but if you want to say this is turbulence, you know who studies turbulence as pure turbulence? Mathematicians, not even physicists, for sure not engineers. We just use those correlations, but some things we know, and I want you to know what is intuitive about them because we can act on them, and we can have coefficients, and we can have formulas that help us predict it. So this onset of turbulence, so the onset of turbulence is for Reynolds X. Reynolds, right? That means would be rho v x over mu. Okay? Yeah. We're going to see that eventually that comes down to diameters too. But for now, let's stick to this. And this is, when this is 5 times 10 to the 5. This is awesome because I'm giving you such a clear cutoff. This is what we're going to be using in class. 5 10 to the 5. More than that, you tell me turbulent. Less than that, you tell me laminar. And wink, wink, you realize reality is more complex than just giving you this ballpark number, because turbulence is not such a trivial thing. Things like roughness matters. Things like upstream turbulence matters. You might have very small turbulence. So we are going to use this value, and probably this is what you're going to keep using the rest of your lives. But if you need to get serious, if this matters a lot, this transition, you should know this is not a mathematical certainty. this is something that has been proven to work often. There is something else interesting. So if I say that the boundary layer, if you remember, was defined by the transport, right? By when we would transport viscosity up to the level of the velocity out here, or when we would transport heat to the point in which this reached the T infinity, right? So there's something interesting about these turbulent boundary layers, because if advection dominates, now I can be very thermally conductive or very not thermally conductive, or very viscous or very not viscous. But if I'm dominated by turbulence, what dominates the transport is the advection. And in the end, what happens is we have the same thickness for both boundary layers, because advection dominates. So, because advection dominates, YCT is more or less the same as YCV. That's important. So the thickness is more or less the same. And if we have this turbulent enhancement, right, the way we're going to calculate things is using effective values. So we're going to say, I know what nu is, or I know what alpha is. But I know that there's more to it than just the alpha or just the nu, because I have advection too, right? And empirically, people find out what this enhancement should be. This is not in the book, but I'm going to give you like effective values. Must use effective values. Right, so this is for viscous transport, right? The effective value compared with the normal value is 14.38 So that means the effective value here at the onset, this is Reynolds critical, right? At the onset, right here, right? The effective value is like 14 times the molecular value. And similarly, right? Remember when we said nu salt is HL over K, right? Now you'd use this with this K effective would give you the heat transfer through that boundary layer. So if we put this together, sorry, here is Prandtl to the 1/3. And that Prandtl to the 1/3 is what comes from the correlations in the books. I'm still not too certain, because if they say that the two boundary layers are the same thickness, it shouldn't be 1/3 or it shouldn't be 1/2. I think it should be something else. But in the meantime, we're going to use what goes with the book. Prandtl to the 1/3 there. So this is laminar. This is turbulent. And I'm going to be using here a different notation. I still need to translate some of this into the book. This is delta, right? And delta, right, is this is not an exact correspondence, right? But this is what delta is. And in this case, this is And this is not a multiplication sign. This is an x. And this is in the book. This is equation 7.17. Right? I'm going to draw something else too. So that's why I haven't labeled this axis. But this is delta, which is the location of 99% velocity. It's one of the definitions of boundary layer. Probably if the definition you used when you took the fluid mechanics class. And the catch is I don't have a way of translating this definition for the turbulent into ours. For the laminar, for us, it's a 3. And they used a 5. So it's more or less the same thing. It's the same order of magnitude. But for the turbulent, I don't have it. And this is so what do you get to see here? At the beginning, we have a laminar boundary layer. That's the one you know for Friday, right? And delta, we're not going to be using delta in our exam, but this is what we have in the book for turbulence. So for matching, have to have it here. Delta is more or less the same as YCT, slightly different definition. So if you use that other definition, you get a factor of 5. We used to get typically a factor of 3, right? That's what I mentioned. And now, when it's turbulent, you have this other formula. The interesting thing here is that, well, here you have Reynolds to the 1/2, right? Minus 1/2. Here you have Reynolds to minus 1/5. So this goes like a parabola like here, but this other guy here, right, is fairly flat. And we're going to see that the increase in heat transfer with distance when something is turbulent is fairly small. So much so that in the case of natural convection, if something is turbulent, the convection coefficient doesn't change with position. Very interesting, right? And now I want to talk about the heat transfer, right? That would be Nusselt. And in this case, we would have Nusselt is and then when it reaches turbulence, it gets enhanced, right? You have that the Nusselt number gets enhanced, right? And then it falls much more flat. So in this part here, you have Nusselt of x is 0.0296 Reynolds to 4/5, Prandtl to the 1/3, right? And this is formula Send 30. So what do you get to see here? That at the beginning of a plate is laminar and is very conductive. But when it reaches turbulence, it jumps. Now, if you're making a heat exchanger, would you prefer a heat exchanger that runs laminar or turbulent? Turbulent, that's true, you want that. Now, the problem with turbulent is that the pressure losses are big. So that you have this trade-off between pressure losses and heat transfer. Now, that is something you're going to see when the chemies, you're going to see in the design class. So but typically, heat exchangers are designed to run in turbulent regime. What's the reason that when you hit turbulence, heat transfer is much enhanced? Right? I think that's a cool thing to know. And it comes from this analysis we're doing on the flat plate.